Hello everyone, myself Sai Krishna. Today I'm going to present you about the speed governing system and as well as the modeling of speed governance system. Let us discuss about it. These are the contents I'm going to present in this presentation. Those are introduction, turbine speed and governing mechanism as well as the mathematical modeling of the speed governing system. So firstly, the turbine speed governing system. The speed governor is a main primary tool for the load frequency control, that is LFC. The figure, which is of the latest slide, shows the schematic arrangement of speed governing system used on steam turbines to control the output of the generator to maintain constant frequency. The speed governing system consists of five parts that are a speed governor, linkage mechanism, hydraulic amplifier, speed changer interconnected with the power system. Here you can see the diagram of a turbine speed governing system. You consist of all models which consist of a speed changer. Here you can see the lower and as well as rise. And here you can see the different parts like different nodes, which is A, B, C, D, E. You can see the junction, you can also call, and here you can see the speed governor of uh, the pilot valve as well as high pressuring oil, and here it is a main piston and hydraulic amplifier. Here you can see the steam, which is like closed and open. So what happens here exactly? So when there's a change in the speed, like raising or lowering, the change in these pointers also changes. That is, when it is raised down, there will be an elevation in the sea as well as there will be a downside towards the D. And due to this, and we have an high pressuring oil over here. So due to this, there will be an opening and closing, that is which allows the steam towards the turbine. So in this way, so when there is a high load, the uh, speed governor, the beams will be towards away from the speed governor, and these rotate when there is a high load as well as when there is low. These two come together. So in this way, turbine speed governance system works. So the first model is like a flyball speed governor. So here you can see that there are two flyballs which are towards with a supporting rod, and it which is connected towards an which is the heart of the system, which senses the change in speed or frequency. As the speed increases, the flyballs move outward, as I said, and these moves outward, and at the point B of the linkage mechanism moves downwards. The reverse also happens when the speed decreases. That is, these flyballs come together towards the rod. In this way, the flyball speed governance system works. And hydraulic amplifier. It comprises of a pilot valve and as well as a main piston lower pressure level pilot valve. There is a movement which is converted into a high power level piston valve movement. It is necessary in order to open or close the steam valve against high pressure stream. And there is also a linkage mechanism, like ABC is a grid link pivoted at B, and CDE is an another rigid link pivoted at this link mechanism, which provides a movement to the control valve and in proportion to the change in speed. It is providing a feedback of the steam valve movement and speed changer. It provides a steady state power output setting of the turbine. Its downward movement opens the upper pilot valve so that more steam is admitted to the turbine under steady conditions. That is, hence steady power will be more towards the output. The reverse also happens, that is like upward movement of the speed changer. And next model is model of speed governance. So let us assume a system which is initially operating under steady state conditions. The linkage mechanism stationary and the pilot valve is closed. These are initial conditions where the steam valve is opened by a definite magnitude. So the turbine is running at a constant speed with the turbine power output balancing the generator load. So let these operation conditions are characterized by the we have given the system frequency as f, and this is generator output, that is turbine output, neglecting the losses of the generator, and as well as steam valve setting. We obtain a linear incremental model around these operating conditions. So let a point A on the linkage mechanism be moved downwards by a small amount of delta Y, and it is a command which causes the turbine power output to change and can therefore be written as an interconnected power system of 1. So the change, that is delta Ya equals to Kc into delta Pc, where this is the change in generator, and delta Pc is a commanded increase in power. The commanded signal, that is delta Pc, which is also written as delta Ye, sets into motion of a sequence of events. The pilot valve move upwards, high pressure oil flows onto the top of the main piston, moving it downwards. The system valve opening consequently increases. The turbine generator speed increases, that is the frequency goes up. Let the model of these events mathematically. Let us see one by one the mathematical equations how this happens. Two factors contribute the movement of the particular C, that is delta Ya, which contributes L2 by N1 into delta Ya, or like it moving upwards, that is K1 Kc delta Pc. So next one is increase in frequency, that is delta F, causes the flyballs to move outwards, so the B moves downwards at a proportional amount of K2 or delta F. The consequent movement of C with a remaining fixed delta Ya is plus or like L1 plus L2 by L2, and K2 dash into delta F equals to plus K2 delta F, that is downwards. The net moment of C therefore is given as delta Yc equals to minus K1 Kc delta Pc plus K2 delta F. Let us put it as an equation, and the moment of D, that is delta Yd, or change in the D position, is the amount by which the pilot valve opens. It is contributed by delta Yc and delta Ye, and can be written as delta Yd equals to L4 by L3 plus L4 into delta Yc plus L3 by L3 plus L4 into delta Ye. So the movement of this delta Yd, depending upon its sign, opens onto the ports of the pilot valve by admitting high pressure oil into the cylinder, thereby moving the main piston opening the steam valve by delta Y. Certain justifiable simplifying assumptions which we can be made at the stage are these are the assumptions should be made, or to have the easier calculations for our modeling. Those are like in inertial reaction forces of the main piston and steam valve are negligible compared to the forces exerted on the piston by high pressure oil. Because of the first assumption, the rate of oil admitted to the cylinder is proportional to port opening delta Y. The volume of the oil admitted to the cylinder is thus proportional to the time integral of delta Y. The moment of delta Ye is obtained by dividing the oil volume by the area of cross section of the piston. So delta Ye equals to K5 integration to 0 to T, and which is negative of delta Yd into dt. Let it mark as an equation of another equation. So it can be verified from the schematic diagram that a positive movement of delta Yd causes negative, that is upward movement of delta Ye, accounting for a negative sign. So this is the reason why negative sign has upward. And here are the, by taking a Laplace transform for the above equations, we can get like delta Yc equals to minus K1 Kc delta Pc of s, as well as plus K2 delta Fs, and delta Yd of s is K3 delta Yc plus K4 delta Ye, and delta Ye of s equals to minus K5 1 by s of delta Yd. So eliminating the delta Yc and delta Yd, we can write the overall equation as delta Y equals to K1 K2 K3 into delta Pc of s minus like K2 K3 into delta f by k4 plus s by ks. So the final equation we get like delta pc minus of s minus 1 by r delta f into ksg by 1 plus ksg. So in this way, the governor model has a mathematical modeling which is essential for knowing the sudden frequency changes and where the movement of the turbine or any losses in a. And here you can see the after the equation, that is R equals to K1 by Kc, which is given as speed regulation of the governor, and the Ksg equals the gain of the speed governor, and as well as Ks is the time constant of the governor. So the equation, when we consider into a systematic speed governance system towards a control system, we can draw the control system as this figure delta Pc towards a controller to Ksg by 1 plus Tsg of S, which gives an output of delta by E, where there is also a feedback of Fs, which is 1 by R given to the controller. So in this way, the modeling of the speed governor is done. Thank you.